Modern machine learning is remarkably efficient at finding associations in vast amounts of data. Give a deep neural network enough passive observations, and it will accurately predict outcomes based on established patterns. But this architecture has a severe limitation. It is mathematically blind to the physical consequences of an active intervention. This associative process mirrors what cognitive psychologists call System 1 thinking. System 1 is the fast, heuristic mental machinery our brains evolved to quickly recognize patterns and ensure immediate survival. Take a look at this sequential drawing. When we observe one action preceding another, System 1 automatically infers a causal link, ignoring other possibilities to jump to an immediate conclusion. Contemporary statistical inference, Bayesian networks, and large-scale deep learning models operate on this exact same cognitive heuristic. They are effectively hyper-scaled versions of System 1, mapping associations based strictly on what is observed. In computer scientist Judea Pearl's framework, this is known as the first rung on the ladder of causation. As you can see here, the bottom rung is association, or seeing. It relies on calculating conditional probabilities purely from existing data. Because of this, passively collected data, regardless of its immense volume, cannot simulate physical reality. It cannot answer a simple what-if question because the data itself contains no information about the mechanics of change. Scientific research requires a different approach. We need to answer interventional queries. We need to know exactly what happens to an outcome if we were to actively alter a specific treatment. This moves us up to the second rung on the causation ladder. Here we reach the level of active intervention, or doing. Mathematically, this requires a transition from standard conditional probability to the do calculus, a framework that models the explicit act of forcing a variable to change. Making this transition requires what is known as System 2 thinking. Instead of relying on automatic data associations, we have to deliberately inject explicit scientific domain knowledge into our framework before we collect a single data point. We map this domain knowledge using a specific structural tool. We construct a causal diagram, formerly known as a directed acyclic graph, where explicit directional arrows define exactly how variables influence one another. When we map out these causal structures, they reveal a mathematical reality that directly contradicts how statisticians are traditionally trained to handle control variables. Ascending to the second rung of causation is not a matter of gathering a larger dataset. It requires using strict structural logic to override our instinctive desire to adjust for every variable we see. Every causal diagram is constructed from 3 foundational junctions that dictate the precise flow of data between variables. The first is a chain. Here, variable M sits directly on the causal path between the treatment X and the outcome Y. M acts as a mediator. When dealing with a mediator, there is a rigid rule. To measure the total effect of the treatment on the outcome, you must never control for the mediating variable. Controlling a mediator is equivalent to closing a physical valve. It mathematically blocks the exact causal flow, rendering your data useless. The second junction is a fork. Variable C acts as a confounder, bleeding influence into both treatment and outcome. Here, the rule is the opposite. You must control for C. Shutting down this backdoor path eliminates spurious correlations, isolating the direct causal effect. Standard statistics is highly effective at identifying forks. The error occurs when researchers apply those exact same adjustment techniques to chains, accidentally destroying the causal signals in their own models. The third junction is the most counterintuitive. It is called a collider. Here we have 2 completely independent variables, X and Y, that both point to a shared outcome, L. In their natural state, the 2 parent variables in a collider are mathematically independent. They have no relationship to one another. The danger arises when you attempt to control for a collider. Controlling this variable forces a conditional dependence. It actively rips open an artificial backchannel between 2 unrelated things. To see how this works in practice, imagine a scenario where acting talent causes someone to become a celebrity, and extreme physical beauty also causes someone to become a celebrity. In the general population, talent and beauty are completely independent traits. But watch what happens if we control for the collider by restricting our dataset to analyze only famous actors. Take this photograph of Vin Diesel. If an actor in this restricted dataset lacks conventional physical beauty, the mathematical model is forced to conclude they possess extreme acting talent. The model generates a spurious correlation between the two traits. The over-control fallacy is a severe mathematical hazard. Controlling a collider actively manufactures false realities, creating relationships in the data that simply do not exist. To determine exactly what to control and what to leave alone, causal inference relies on a universal rule known as the backdoor criterion. Look at this diagram. The criterion states that you must block all non-causal paths entering the treatment variable while leaving all causal paths open. Because there are no arrows pointing into X, there are no backdoor paths in this specific model. The analysis changes when we apply the criterion to a more complex structure, like this M-shaped causal diagram. Here, the central variable B sits precisely on the only backdoor route connecting the treatment X to the outcome Y. Because B has two arrows pointing into it, it is a collider. Colliders naturally block the flow of data on their own, so the backdoor path is already closed. You do not need to control for anything. If a data scientist instinctively controls for B, they pry open the backdoor path, introduce spurious correlation, and completely ruin the model. Causal diagrams provide the mathematical proof that under certain structural conditions, doing absolutely nothing is statistically superior to applying standard adjustments. This structural logic perfectly explains a famous historical error in medical statistics that baffled researchers for decades. In the mid-20th century, statistician Jacob Yerushalmi conducted an observational analysis on maternal smoking, infant birth weight, and child mortality. His data revealed a paradox. For severely underweight babies, the mortality rate was inexplicably lower for infants of smoking mothers compared to non-smokers. We can map this problem structurally. Smoking and unmeasured genetic factors both point to low birth weight and down to child mortality. Yerushalmi's structural flaw becomes instantly visible. Low birth weight is a collider between maternal smoking and severe unmeasured genetic factors. The birth weight paradox completely lacked a biological explanation. The anomaly was purely a mathematical artifact caused by methodological overcontrol. Controlling that collider created a fatal illusion. Researchers artificially restricted their analysis to only look at underweight babies. This forced conditional dependence, accidentally opening a spurious, non-causal backdoor path, flowing from smoking, through birth weight, up to unmeasured factors, and down into mortality. If an underweight baby had a non-smoking mother, the model automatically inferred the presence of unmeasured, life-threatening genetic defects to explain the low weight. Because the non-smoking mothers had babies with these severe genetic factors, the babies of the smoking mothers appeared artificially healthier strictly by mathematical comparison. The moment you apply System 2 structural logic, the paradox vanishes. The diagram explicitly warns you not to control the collider. Data-driven decision-making is structurally blind to reality if it operates without a causal model. Algorithms can only process what is present in the dataset. Causal diagrams allow us to encode scientific assumptions, test those assumptions mathematically, and dictate exactly which variables we must leave alone. To build true artificial intelligence and conduct rigorous scientific inference, we have to move beyond observing passive associations. We have to map the structural mechanics of how to actually change the world.